Should I start now, or?
Yeah, sure.
Okay. Can everybody hear me? Is this mic on?
Yeah,
Good.
it is fine.
All right.
And there's a pointing of the arrow city on my
I got it right here. Hello, my name is Jeremy McMinis. I'm a grad student here. I think I've introduced myself once before. So I'm going to talk about wave function optimization in VMC, and the approach that I'm going to take is really from the VMC perspective. I'm not going to talk much about how the wave function changes. I'm not going to talk much about the diffusion Monte Carlo aspect. That's something that we can talk about later. I have a final slide that says something about that. But my basic approach is going to be to talk about these four things. I'm going to start with the motivation for optimizing the trial wave function. I'm going to go through a history of wave function optimization, and this will kind of be like short journal club kind of talks. I'll talk about the original VMC calculation that McMillan did back variance minimization that was pioneered by Cyrus Umrigar and coworkers. And then I'll talk a little bit about the energy minimization algorithm, the things that we do in our code QMC pack. And I'll end up with an example of something that we're able to do using multideterminant expansion and these modern wave function optimization algorithms. So the talk probably will not last until 12:30. So if you have questions, please feel free to ask them, and I'll try to answer. So in variational Monte Carlo, we're going to compute observables over a trial wave function. The form of the integrals that we actually perform look like this. We find the expectation value of some operator O averaged over a trial wave function psi squared. This defines a probability distribution that we sample. And so I'll use this notation throughout the talk in order to and whenever I use this, what I mean is that I'm performing this integral. I'm performing the integral of the expectation value of some operator applied to a trial wave function averaged. And the thing about performing these integrals in variational Monte Carlo is that the trial wave function is absolutely everything. It's the only thing that you get out of your observables are the things that exist in the trial wave function. So it's absolutely essential that the trial wave function that you use has the right physics in it in order to get the values of the observables that you're looking to compute and to have them be close to what we would observe in experiment. So this motivates us to think about what are the errors that we make in the observables based on the error that the trial wave function has. One of the most important observables that we regularly compute is just the energy. We could do equation of states, binding curves. Many different things are just functions of the energy of the system. And these integrals we take, I'll denote this as E sub v is the variational energy in VMC. It's the expectation value of our Hamiltonian. And we recast this Hamiltonian in the form of a local energy operator by applying the Hamiltonian to the trial wave function and then dividing back through by the trial wave function. And this gives us this expectation value that we're computing. And so this Hamiltonian, of course, is the kinetic plus potential energy and any other terms that you would have in it, pseudopotentials, for instance. So in order to investigate what the trial wave function error is, what we can do is we can take our trial wave function and we can expand it into two pieces. One piece is the exact wave function for the system that we're interested in, and then some residual error. And so if we take this trial wave function and its error and we insert it back into our original expression, we can compute two things. We'll compute the error in the energy and the variance of the energy. So the error in the energy is just the expectation value, the local energy minus E0 averaged over the trial wave function squared. And we can see that after we plug this in and do a little bit of algebra, you'll see that the error is second order in the trial wave function. And the variance, which is an important quantity as well because this controls the statistical efficiency of our variational Monte Carlo algorithm. With a smaller amount of variance, we're able to compute these expectation values with smaller error bars and a much more rapid time. So if we take the expectation value of the local energy minus the ground state energy squared, then we'll see that this error goes also as second order in the trial wave. So this is actually great. This is one of the reasons that variational Monte Carlo works so well, because the error that we make in the energies in our observables are second order in the trial wave function error. But this wave function error, it still exists, and it's something that we want to minimize. For generic observables, other than the Hamiltonian, these error properties are a little bit different. Whenever we apply the Hamiltonian to the ground state wave function, it just returns a constant number, which is the energy, times the trial wave function. It's an eigenstate of the Hamiltonian. But trial wave functions are not, in general, eigenstates of observables. So whenever we compute expectation values of observables over the trial wave function squared, the error is actually larger because we're no longer allowed to commute the operator through the ground state trial wave function in order to eliminate those pieces. So whenever we compute the error in observables, we get a contribution that goes first order in the trial wave function. And for the variance, we get a piece that is just of order 1. And so in order to try to combat this problem, there's two different approaches. One of the approaches is that we can improve our estimators. There's an entire formalism based on the Hellman-Feynman theorem that we can use in order to reduce the bias and the variance to that of the energy calculations, second order in the trial wave function error. But there still is a residual error, just as in the energy case. So even after we do that, we still have to improve the quality of our trial wave functions in order to compute accurate observables. So this is a plot I believe David showed yesterday from his paper where he looked at, this is the two-dimensional electron gas using a variety of different trial wave functions. And here what we plot is we plot the variance on the x-axis times some factor, and then the y-axis is energy. And so we can use a Slater-Jastrow wave function, Slater-Jastrow with 3 body terms, backflow with 3 body terms, and we'll plot energy versus variance. And so the motivation for doing this and projecting to the zero variance limits, actually, it's very well motivated, because we know that the error in both the energy, here's the energy, and the variance goes like delta psi squared. So this is a linear relationship between the two. And we assume that if the variance goes to 0, then that is, in fact, a reasonable way to estimate what some perfect trial wave function could provide. Of course, there's some statistical error in this. Optimization can give you slightly different parameters if you do energy or variance minimization. But if the entire thing is consistent in the way that you do your calculation, oftentimes this is a reasonable way to extrapolate.
Can you just comment why is the variance in DMC 0?
So this is just a reference calculation. So if you look at the way that the variance of this calculation goes, it's actually not second order in the trial wave function error. It's a product of the error in the fixed node wave function and the error in the trial wave function. And this is, I believe, put in this position just to illustrate how the DMC algorithm gets you to the best ground state.
It's not easy to compute the variance, because remember, in fixed node, you're solving the Schrödinger equation exactly in these nodal pockets. So zero variance there.
Right.
But you have a mismatch of the derivatives across the nodes, but we can't calculate that easily. And so there's like a delta function variance sitting on the nodes, but the probability of sampling that is 0, so it's not something we can easily calculate in fixed node. So we don't know what to put for the variance. I mean, you could develop a whole technique just to calculate that, but it seems nobody's ever done that.
And you can use different quality of trial wave functions and plot them as well, and they'll give you slightly different energies here as well. So this, I think this is more of a suggestion as to how accurate the DMC is, or I'm not exactly sure what to say.
Well, it's kind of
No?
It's not, it's not mathematically true that those things have to lie on a line. I mean, you can easily make a counterexample. But it's interesting that they actually do lie on, there's an empirical relationship, as you said. If you take families of wave functions that systematically study, they do lie on a line, and they give you an idea of how bad, your energy might be, right?
Yeah.
Well, wait, if you had like the perfect wave function, like with VMC, you should get zero.
You would get there at that point, that's true.
But no, but in that case, it might disagree with but the backflow is not perfect, right? I mean, because that still depends on your
Yeah.
trial function. So unless you use the same perfect function, if you use the same perfect trial function, they should agree.
I'm not sure what your point is.
No, my point is that if you have the perfect trial function for VMC, you should get zero.
Yeah, you should be,
And if
you would have
should
solved
get
the
the same
problem.
result with DMC, if you have the perfect trial function.
It'd be the
Yeah.
same. Yeah.
Right,
Yeah,
did the
yeah.
same, so that's my point.
Wait,
Yeah.
You were saying they don't fall on the line necessarily, but.
okay, if you go back to that slide, you could get some points. For example, it's very easy to make the variance higher and keep the energy about the same. So you could make a wave function, you could add some little wave noise,
Oh, yeah.
increase the variance, and then the points would shoot over to the right.
But then there should be some envelope. It's like the with this
Yeah,
line.
that's right, that's right. There's things you could say, but it's not so simple.
Okay.
So hopefully there's some motivation for, so there is some motivation to optimize the trial wave function in order to calculate more accurate observables. So now what I would like to do is just kind of go through 3 different wave function optimization techniques. These are just in order of history. The first one is by hand. If you have a very few number of parameters, you can just compute the energies for them and find the minimum. The next one was a variance minimization, and then the last one I'll talk about is the current state of the art, which is the energy minimization using the linear method. So this is the first, to my knowledge, the first big VMC calculation. It was done by Bill McMillan here, published in '65. And this is actually really a very nice paper to read for a student, especially. It's very pedagogical. Everything that's done in here, he has to justify and explain. And he has to do everything. So he has to choose a trial wave function form. He has to choose a specific function in order to use in his trial wave function. He has to optimize it. He has to figure out how the most efficient way to compute observables, such as the momentum distribution, is. He has to do, everything that he does in here, he explains because there's nothing that he can really cite in order to, say, oh, look at this is how I did it. No, this is actually, everything that he did was in here. And so in the paper, he looks at the ground state of liquid helium. And, well, I'll go to the next slide. So the part that I'm interested in talking about is just the wave function optimization part and kind of how he chose the specific form of the wave function that he did. So in this calculation, at that time, whenever people did calculations on helium, what they really used was the Lennard-Jones 12.6 potential. The Lennard-Jones potential is this form where you have 1 over r to the 12 minus 1 over r to the 6. So it's got a strongly repulsive core, it's got a narrow well, and it's got this asymptotic tail that goes to 0. And so so the wave function that he chose is of this product form. So we're using, this is a bosonic calculation, helium-4 is bosonic. So this obeys the Bose statistics whenever you exchange any 2 particles. There's no additional sign generated here. And there's 2 other nice physical motivations for choosing this form. One of them is that in the very, very low density regime, the exact wave function can be shown to take this form. And that was a result of, I believe it was Landau and another Russian, Zubarov. But in addition to that, you can also show that if you do a low density energy expansion, that this form will take care of the first 2 terms in that expansion. So after he chooses his trial wave function form, he needs to find a specific form of f in order to use in his calculations. The form of f that he uses is this exponential that has two parameters in it. One is a1, the other one is a2. So the physical motivation for choosing this form of the wave function is that, so for distances that are very small, you expect that the trial wave function form will essentially it should look like a solution to the two-body Schrodinger equation for that potential. And so at the very small, in the small limit, that is true. And then as r gets large, as the particles become separated, that it'll essentially become flat, and the particles won't see each other anymore. So using this wave function form, he showed that both of those limits were achieved. And it's some smooth way to interpolate between the two. So then he had the problem of actually optimizing these parameters, A1 and A2. So the way that he did this is the first way to do it, is just by hand. There's only two parameters here. So I can bin up my space. I have A1, I have A2. I can actually just compute the energy for all different values of A1 and A2. So A2 right here is in the exponent. And so for this right here, for computational convenience, in order to not have to deal with log forms, he just chose integers so that he can just square and repeatedly apply this value in here. And here we see for a couple different values of A2, we've got A2 is 4, 5, 6, I believe this is 8, 10. And then for the value A1, this is a continuous variable. And you have some physical motivation for choosing this as well, because it should be close to the value that you would get from the two-body Schrodinger equation at short range. And so I believe that the actual number for A1, if you just look at the very short range, is something like 2.61. And it turns out that the value that he finds that is actually optimal is rather close to that as well. So, you know, when you plot it, he finds that the minimum lies somewhere in here, and he chose a value somewhere in here in order to produce his results that were actually very nice, especially considering the computational resources that he had to apply to that problem. And maybe I should have put a plot of his results here in order to illustrate that. I think typically he found that you can look at the paper and see what the results are. I should have included a slide, but they weren't so bad. So are there any questions on this paper? Is there anything that... It is a very clear paper to read. So in 1988, Cyrus Umrigar, Ken Wilson, and John Wilkins at Cornell wrote a paper that talked about optimizing trial wave functions for quantum Monte Carlo calculations. And the way that they did this was using a variance minimization procedure. And when it came out in '88, it was a state of the art, and it pretty much had linear. The growth in citations was pretty linear up to about 2000, and at 2000 was the point in which like the next set of optimization procedures came out, and at that point it kind of leveled out. But it was a very successful method and allowed people to optimize larger sets of parameters to actually do quantum chemical calculations, for instance. So I'm going to talk a little bit about the trial wave function form. So this is a calculation that Umrigar and Filippi performed, and they looked at first row dimers, nitrogen, carbon, oxygen, and they computed energies and variances for these dimers and compared to the exact results. The exact results are very high-level quantum chemistry calculations with full extrapolation in order to compute the amount of correlation energy that the variational Monte Carlo calculations recovered. So the way that they parameterize their trial wave function is as such. They have a Jastrow that's got a set of parameters, and then they've got a set of determinants with another set of parameters. And you can optimize all the parameters in your Jastrow and all the parameters in the determinants. This Jastrow is typically it's got a couple of different pieces. So you want to put in a one-body term, which talks about electron-ion terms. You put in a two-body term, which is electron-electron. Three-body terms, which is electron-ion or electron-ion-ion, these types of pieces. And some codes go even beyond that to four-body interactions. But in this paper, I believe it was just the one, two, and three-body terms. And so in the variance minimization algorithm, what you do is you define a cost function, C of P. C is our cost function, P is a set of parameters, and C is a set of coefficients that define kind of costs. So we can define C1 will be the cost of E local minus the average E local squared. So this is a variance term. C2 can be the distance of the local energy to some target energy. So you estimate what the ground state energy should be. You set the target energy there or maybe a little bit lower, and then you enforce a cost based on the distance of E local to that target. And so using this method, they could optimize, they could minimize this cost function using anything. You can use your Leavenworth-Marquardt. You can do like stochastic gradient. There's many different ways that you can minimize once you have a well-defined cost function. And so using this, typically people would optimize maybe 10 to 100 parameters. And the results that they got here are actually rather difficult to see. But so on our x-axis, we have the species of from left to right of increasing nuclear weight, nuclear charge. And the y-axis is correlation energy. This point down here is, I believe, 65. Yeah, it's 65. 65%, 75, 85, 95, and 100. There's two sets of lines here. The bottom line is for the single determinant configuration. The top line is for the multi-determinant configuration. So if you just take the Hartree-Fock determinant, optimize the JASTRO, and compute the amount of correlation energy you recover, this is the curve that you get. And using a multi-determinant expansion, you're able to recover significantly more. And you'll see that the variance grows almost linearly as you increase the nuclear weight of the ions, the nuclear charge, sorry. And so this variance minimization is actually very nice because in the complete basis set limit, both the variance and the energy minimization are the same. If I have a complete basis set limit and I perfectly sample, those two results will be identical. But the nice thing is that these pieces that we put into our cost function earlier are positive definite. They're bounded from below. So they're very nice functions that you can use to optimize on using any traditional nonlinear optimization algorithm that you want. You don't have to worry about unboundedness. But the problem with just using energy, which naively is the right thing to do, is to minimize the energy, is that it's not bounded from below on a finite sample. And here I have this very simple example of a hydrogen atom in the crazy extreme limit of a single Walker. So if I just choose a place at random and put an electron down next to a hydrogen atom, and I write down a trial wave function looks like e to the negative PR, and I'm going to optimize this p. And I just want to see, what will my variational energy, what will my energy of this configuration be if if this is what I choose. So I'll just say R is epsilon, and then I'll just write my local energy as a function of this parameter in epsilon, and I'll subtract the real ground state energy of the hydrogen atom off. And so the result is like minus p squared over 2 plus p minus 1 over e plus a half. And so you find that your optimal value just depends on what the point was that you had sampled originally from your distribution. And if you take this functional form, you can see that you get something that's like 1 over epsilon, 1 over 2 epsilon minus 1 plus a half. So if epsilon is less than 1, you can see that this term, you can choose, if you choose your epsilon small, this can go negative, all right? So in this case, you can find ground state energies for a single sample that are actually lower than the actual ground state energy. Of course, as soon as you put that parameter back into your trial wave function and generate some reasonable set of samples, you'll find that this wasn't true at all, that you have actually a very terrible wave function. You have a very poor estimate. Similarly, you can take, minus p to the r squared. You could use a Gaussian, and you could look at the other piece where you have like the single basis set and look at how your energy is there if you optimize on energy or variance. So all was not well with variance minimization, even though it gives it's a very reasonable thing to do. Oftentimes, the values that we calculate, energies and observables, are not the best ones that we could compute with that trial wave function form. There is some work by Snyder and Rothstein in 2000 where they looked, maybe I can make this bigger. Well, the basic point here, I'll show you. So these are energy optimized and these are variance optimized wave functions. And they compute some mean error. And the mean error for the energy optimized over this large set of observables, moments of electron distance from the cores, electron-electron moments, they find that the error is like 0.85 in the case of energy minimized, whereas for variational minimized it's 1.3. So you actually do get much better trial wave functions and more accurate observables if you use energy minimization instead of variance minimization. So this prompted more work on doing the actual energy minimization instead of using variance. So I apparently have made all my plots too small. That's rather unfortunate. So in 2007, there was a PRL from Umagara, Toulouse, Filippi, Sorella, and Hennig that was actually a collection of algorithms that had been developed previously over the last maybe 6 years. And they were algorithms that were based on a generalized eigenvalue expression to minimize the energy of the trial wave function as opposed to the variance. And so they got some very good results. So here, it's very difficult to see. I apologize for that. But so on our x-axis is essentially the number of parameters in our trial wave function. The y-axis is energy in Hartree. And the blue line is the DMC, and the red line is the variational Monte Carlo. And so this system is carbon-2 with the JASTRO, CSFs, orbitals are optimized. It's a pseudopotential calculation. And you can see that the energy for VMC goes down as you increase more parameters in your trial wave function. And they're actually able to get rather close to the exact value, which is 11.102. This is a carbon dimer, and it's using I think it's the Burke-Filippi-Dole pseudopotentials.
By the way, your PDF is fine. Your solution of PDF is just great.
Okay.
It's just a project or whatever.
Okay. All right. So yeah. So if you can look at this on your computer, it'll look much better. So yeah. So they found that they could compute the binding energy of the C2 molecule to experimental accuracy of 0.02 eV. So the linear method gets its name from the way that you treat your trial wave function. What you do is you take your trial wave function and you expand it. So okay, so here is the, we're going to use a linearized trial wave function. This trial wave function consists of the trial wave function with a set of parameters in it, plus a set of basis states. These basis states are built from the derivatives of the trial wave function with respect to the parameters evaluated at the parameters that are currently in the trial wave function. So this really is just a Taylor series expansion to first order in the wave function derivatives. Now, the second thing that you do is you orthogonalize it to the trial wave function so that you subtract out from each of these individual psi i's their overlap with the ground state wave function so that you really have a basis that it's linear and it's orthogonal. And then you have, if you have, NP parameters, you have NP of these basis sets, NP of these basis functions that you're optimizing into. The generalized eigenvalue is built up just out, you evaluate your Hamiltonian in this basis and your overlap matrix in this matrix to find a new set of parameters. The way that this is formulated, the thing that you find that you solve for, these delta p's, are the difference in your optimal, your new set of parameters, and the set of parameters that you had the previous step. So it's an iterative procedure. These matrix elements and what they actually consist of are it's the inner product of psi I and then h psi j and psi I psi j. So this matrix element, if you look at it closely, you'll see that it's not symmetric in I and j. So, and this is something that gives it a strong zero variance property whenever you compute these. These psi i's are the rows, and then the columns are the j's. So, do I explicitly? Yeah, I don't. So if I look at my wave function, my 0, 0, well, in C notation, this would be the 0, 0 element. And then as I go this way, I get psi I, h psi j. And the same thing here. But here I get basically, what I'll get is I'll get something that looks like this. So I'll get the trial wave function psi I applied to just the local energy, whereas over here, and this will be psi I h psi j. So the elements that are here are different than the elements that go this direction. And so I end up building a matrix that is non-Hermitian. The noise in the off-diagonal elements is not correlated. And this is what gives me a better estimate of what this, for this matrix. So, so in addition to this, you can perform stabilization by adding some small overlap parameter to the diagonal elements that aren't the 0, 0 element. But this is a detail. So if you have linear method, if you have linear parameters, so for instance, you're just doing, you want to optimize a multi-determinant expansion, and the only thing that you have in your wave function is just a set of linear parameters times determinants, then you can just, you solve your generalized eigenvalue problem, you find these delta p's, you apply them to get a new set of parameters, and you're done. It's exact in this basis. So it's very, very nice whenever you're looking at something that is just a multi-determinant expansion that doesn't have anything nonlinear in it. Of course, there may be some additional error in the sampling, so you do want to iterate a couple times to make sure that you're there, but in theory, I believe that it is exact. So if you have nonlinear parameters, though, then things are slightly different. So when you have nonlinear parameters, you have this unknown normalization factor for your trial wave function. And oftentimes in VMC, we work with unnormalized trial wave functions because it's not easy to compute normalization factors whenever you have a Jastrow times a determinant. I believe that computing the normalization for a wave function is like computing a free energy. So it's very expensive. So if I look at what these psi i's become whenever I add the normalization factor, I'm just going to explicitly add n of p here. And this psi will just to denote that it does exist. Once I take the derivatives with respect to p of I and then orthogonalize with respect to the trial wave function, and look at the new linearized wave function, I have the wave function that I started with plus some normalization factor of p times the same delta pi psi I piece. Well, this n of p is not really is not known. So whenever I take a set of parameters, I solve for a delta p. Well, that delta p that I change in here will change an overall scale factor for these basis functions. So then it allows me to put an additional alpha into my solution for the parameters to account for this overall rescaling as the normalization changes.
So why is the derivative with respect to n1?
So it's not. So I get a term out that looks like. So I say d dpi. Here's my n and here's my psi. So I get dn. I'll just look at this term, and then I get this other term that's like n, like this. Well, in step 2, I find psi tilde, which equals psi I minus the overlap of psi I and the trial wave function times the trial wave function. And so this piece right here is subtracted out when I perform this subtraction right here. So anything that the normalization contributes, the overlap with psi and psi is just 1. And so I subtract off this much of the trial wave function, which exactly compensates for this piece of the normalization function, leaving me with just the other piece, which is this uniform rescaling factor. And so, is that clear? Reasonably?
Yeah.
Okay. We could talk about this later. It's very, maybe I should have wrote it bigger, but. So this alpha, you can set it many different ways. In the original paper, what they do is they just have, they have a heuristic. They say, well, what I want to do is I want to just make sure that the normalization of my new linear wave function is the same as the normalization of my trial wave function. And this gives rise to a way to analytically compute using the overlap matrix and the parameters changing an alpha to apply, which can change the sign of the parameter changes as well. It's not just it's more than a rescaling. You can actually make it go negative. Or you can use something else. You can use something like line minimization, because it's just a one-dimensional problem at this point. So at this point, I think that what I'll do is I'll sketch out the algorithm as it's implemented in QMC Pack. And there are things in here that, so anyway, there's dragons around, but so we can start off by defining some cost function. The cost function now, it can have energy in it. It can have variance in it. It can have whatever else terms you want. There's like an unreweighted variance in it. Anyway, so you define this cost function. So over the optimization, when you optimize, you evaluate your cost function. And if you are decreasing, if your cost function is decreasing from the last step, then you continue. But whenever there's some threshold so that you don't improve your energies, if your energies don't improve enough, you say, okay, well, I'm done. It's all statistical error now. I'll continue. The first thing that you have to do is you have to run the variational Monte Carlo in order to fill the Hamiltonian matrix and the overlap matrix. And while you're doing it, you generate a set of walkers. And so this set of walkers are just stored configurations of electronic coordinates. You can, and we'll use them again later in order to perform the rescaling procedure. So once we have sampled these to sufficient statistical accuracy, we can either put like an error bar on these if we would like, or we can just sample a certain number of steps. We'll invert the S matrix, apply it to the Hamiltonian, and now we just have an eigenvalue problem, no longer generalized. And we can and we'll solve this. But we'll have some constraints on our solutions. Because this can be, because we have something that has stochastic error in it, this is something that can be poorly conditioned. So it's entirely possible that in some cases we find our lowest eigenvalue solutions are actually are very large parameter changes. But we know that we're close to the right answer. We start from something that's reasonable. So we want to make sure that we stay in the same quadratic basin. So while the maximum parameter change is greater than some maximum allowed parameter change, we will add this stabilization factor. This is effectively rotating from this is kind of like a Levenberg-Marquardt type of procedure that is performed. You're taking your Hamiltonian matrix and you are increasing the diagonal except for the zero element, and this will rotate you from kind of a Newton's direction where you're solving like a del squared over del to something that looks more like steepest descent. As you increase this overlap parameter, your steps will get shorter, and they will get and they'll be more in the direction of what the gradient is for those trial wave function parameters. Okay, so then once we have performed the stabilization process, we'll solve the eigenvalue problem and get a set of parameters. If they're acceptable, then the next thing that we'll do is we will minimize the cost function using some rescaling factor and the set of parameters that we solved in our equation. So this is a vector that defines a direction in a one-dimensional space. So we can evaluate our cost function. So there's many ways you can perform this step. You can use the rescaling technique, as I mentioned earlier. You could just bust out your numerical recipes and just put in any of those algorithms that you like, BFGS, or the thing that we choose typically is we do like a quartic fit. We'll evaluate this cost function in several places. We'll fit it to a fourth order polynomial, and we'll find the minimum that way and then evaluate it. So for unreweighted variance, and whenever we're very close to the minimum, this works very well. And it's less expensive than doing a full line minimization because it only requires some fixed number of evaluations. Of course, the fastest thing to do is to rescale. You just have some analytic formula, you update it, and move on. So whenever we do the quartic fit, there's also several ways that you can evaluate those points. The thing that we choose to do, well, there's two different ways you can do it, but the way that we do it is we evaluate this cost function over the set of walkers that we generated during the VMC. This saves time. This is computationally efficient. We already have a set of parameters, and if we're smart about it, we can save a lot of other things from those walkers that will be useful as well, all of our distance tables. If we're just optimizing a Jastro, then we can carry around the determinant values. We don't have to evaluate the determinant again. So there's some computational advantage for using a fixed set of walkers. Of course, that's not essential. In the original papers, they actually did a full correlated sampling routine, and where they actually ran VMC with all the different parameters, and then used that to get the new set. Then at the end, we have our new cost function at the minimum that we computed, and we evaluate it and loop again if we have to. And that's the basic structure of the, yes?
Yeah, I have two questions. So if you multiply h by s inverse, do you still have to solve a generalized eigenvalue problem? Shouldn't you just be solving the...
This is a misprint. You're absolutely right. Now we've applied this to this side. And so it's, yeah, I apologize. That's absolutely right.
And I have one other question. So usually, like in optimization algorithms, right, you do this step of kind of regularizing, in this case, your Hamiltonian, but whatever Hessian, right, would normally be, to get better directions. And then the second step, right, is the line search is to limit the step size, that you don't get too far away because you only can guarantee local convergence. So do you do some check on this alpha that it's not too large?
Yes, actually, this should actually be indented because there's two checks. First I solve this. So first I solve this and I check. Then I solve this and I check.
Okay.
Yeah.
All right.
And so I check both of those. Yeah. But if this part does not, if this part does not satisfy this, I don't try this at all. But if
Yeah.
it satisfies it, then I will try it.
Yeah.
Yeah.
Okay.
Oftentimes, and what happens is that as your intuition suggests, whenever I just barely satisfy this for my eigenvalue equation, and I go to do my quartic fit, it's not good, and so I have to actually redo it again. But there's parameters in here. This lambda you can add, and each time that you loop, you can decide to add a little more. You know, it's there's so many free parameters, and choosing how to stabilize that it's just is black magic. You feel it, and you do what you think is right.
Well, yeah,
Uh-oh.
that's not
Black
that's not
magic.
good. No, that's not.
No, no,
well,
no.
no, even
No.
in optimization, that's not completely unusual because this. I mean, it depends on. So a lot of people who write optimization codes, you know, want something that works for everything you throw at it, and so they basically just want to make sure it converges, right? But obviously, if you have a specific problem, you want to tune things for something that works.
The optimal may not be that, and my optimal will be something that works 95% of the time, or?
Well, it usually, so if this first step would be really poor, right? If the maximum of delta p, it probably means you have some sensitivity in there that gives you a really poor search direction. So in terms of convergence, what you need to prove is that your search directions in multiple steps cannot converge to each other. They don't lie in some subspace that's less than n, because then you can get stuck. So in optimization theory, you do this regularization to some degree, only to some minimum amount if you need to guarantee some independence among your search directions. But then in order to make sure that, so it's a Newton-like method, but Newton converges only locally. So in order to make sure that your step doesn't jump too far, you do the line search. But there's huge range of choices there too, so it's not.
So in practice, this lambda is, so the code chooses this reasonably. The default is reasonable, and so typically it will converge. The question is how many iterations it takes to converge. And so for solids or for molecules or for bosons in an optical trap, like the values that you choose for this lambda could be different by orders of magnitude. And so just experience dictates what you start with. Yeah.
What is the typical number of random optimization?
The number of walkers that I generate. Okay, so in the code there's two different there's really kind of two different number of walkers. All right. One of them is the number of walkers that it takes to generate the matrices, and the other one is the number of walkers that you use to perform the line minimization. Okay, so whenever you generate the matrix, typically what you're looking at is a number that is proportional to the number of parameters in your trial wave function. So if you're just optimizing a Jastro with maybe 30 parameters in it, I may be able to use 8,000 walkers. If I'm doing something like a multi-determinant expansion that has something like 10,000 parameters, I may need 1,000,000.
So you're saying like 100 times the number of parameters or something?
Yeah, but it's not, it also depends on the quality of the parameterization, the overlap of the parameters in space. There's the size of the system. So the metric that you actually need is something like number of parameters divided by the number of electrons. You want to know how many times that basis function is evaluated. So it's
Yeah, this whole philosophy was very different than my philosophy was. All those years, I always try to encapsulate all the say 10 parameters, try to figure out each one, what physics it was controlling, instead of just expanding out in thousands of parameters. And so if you have a limited number of parameters, then they become sort of orthogonal to each other.
Yeah.
You can optimize one parameter without messing up the other parameters.
And I think you can get very good qualitative results doing that.
Right.
But if you do a multi-determinant expansion from something in chemistry, like I have no physical intuition for what this particle hole excitation means to nitrogen dimerite.
Right.
So, I have a quick question. So when you're doing this optimization, so you you can, depending on choosing CE and C sigma, you can choose energy only minimization and variance only minimization.
Can you say it one more time? I'm sorry.
So you have CE and C sigma, right?
Yeah.
And you can set, for example, 1, 0 or 0, 1, and
Yeah.
you can have two set of runs
Yep.
in which you do variance only minimization and energy only minimization,
Yep.
and chances are you will get two different wave functions. So,
Slightly different, yes.
so which one?
So this is what we do. The way that we usually bake this is that we'll run, I'll run 2 steps of variance minimization because it's more stable and it'll get me close to the minimum. Then I'll run either 1 step or 2 step of energy minimization. And the energy minimization will be like maybe 97.5% energy and 5% variance, something like this. So that I put a very small amount of variance in it. The basins are not, so let's say this is the basin that our variance lives in, and this is the basis of energy. So that they don't, so there should be some, so I mean the actual minimum of variance may be here, and the actual minimum of the energy may be here. But by adding a little bit of variance, I can improve, without sacrificing much energy, I can improve my computational efficiency maybe some non-negligible amount.
So you choose delta p as an eigenvector of this eigenvalue equation, right?
Yeah.
How do you choose the normalization of that parameter change?
So
Isn't that the alpha?
is this what you're asking, how I choose this alpha? So I get an eigenvalue out, and the eigenvalue has, it's got, you always get a normalized eigenvalue out of like LAPAC. And so then what I do is I compute using like the norm procedure, the procedure that where you conserve the norm of the wave function before and after, to give me an initial guess at what that rescaling should be. Once I have that, I use that as the basis for determining where I perform my quartic fit.
So if you solve an eigenvalue, you get a vector, but the length of that vector, apart from it not being 0, has no meaning. So what is the length of delta p?
You mean
Just
it's the same as the number of parameters plus 1.
Or usually it's normalized, isn't it?
Yeah,
One.
so.
Oh, you mean
yes,
the inner product?
If the max over the delta pi is larger than 7p max, but I mean, since the vector is normalized, isn't
Well-
it always something modest?
Well, I take the, so I take the
So the
rescaling
P-
factor of Ummergars, I apply it to all the parameters, and I find the magnitude of what that change would be if I used Ummergars' algorithm.
Okay.
And if it turns out to be some crazy thing, then, yeah. So it's basically if one parameter changes a lot compared to the others, is kind of what that looks like.
Okay, so it's really a relative thing, because I mean, in principle, you can scale an eigenvector arbitrarily.
Yeah.
So it's really, what you're looking at is not so much whether some component is large, but you're really looking at whether this one component is much larger than the others.
Yeah, so, and that means that you've probably done something bad.
Go ahead.
Okay.
We are starting to impinge on lunch here, so.
Oh, is it? Okay, so I have 2 more slides in the
Okay,
conclusion.
good.
Yeah, yeah, I'm very close. So I was just, so in the paper, I mean in the online you can see this better, but so I'll just give an example, for instance, of some recent results that we've gotten using like a large determinant expansion and the optimization algorithm in QMCPAC. So we have, so there's a way that we can compute massive multideterminant expansions. This form is just the Jastro, and this is just the same form as earlier. It's just that the number of terms in this determinant expansion is much larger than it was before. So previously, the number of terms that you expect to get in an expansion could be something like of order 10, maybe to 100 if you really have a lot of computer time that you want to use on a problem. So there's a way that you can use many more, and it's in this paper, Clark, Morales, me, Kim, and Scusaria, this JChem Phys. And we go up to about 3,500 configuration state functions, which corresponds to about 18,000 determinants. And we performed the optimization, and we can look, in this paper what we did is we just did the all-electron water. We want to compute the energy of all-electron water and compare it to the exact result. So here on our x-axis is the sum of squares of the initial CSF coefficients. On the top, it actually is more importantly, is the number of CSFs that we include in the optimization in the trial wave function. The y-axis here is energy and Hartree. The Hartree-Fock value is somewhere up here. It's not on this. And so starting from the single Slater determinant times the Jastrow and then increasing the number of parameters, we could get to values that are within chemical accuracy. They're very close to the values that you get from like a fully extrapolated CCSD with preparative triples and R12 corrections, for instance. And so, you know, we can, this is, unfortunately, I don't have something to directly compare from earlier, but so here's like a first row atoms, for instance. So these are lithium, beryllium, boron, carbon, and our y-axis is, in this case, correlation energy. Now the lowest point is about 86.
This is VMC?
There's several things. I'll describe those in a second, but I just want to talk about the axes. So this is 86 up to 100. This is the percent of correlation energy recovered relative to the exact quantum chemical calculation. And so there's a spaghetti of lines here, and the ones that I want to point out are, okay, so this work, are the VMC is a set of blue lines that sit right here. This line right here. So these all recover greater than about 98% of the correlation energy across these first row atoms.
With lots of determinants.
With lots of determinants, yeah. And then for the DMC, it's this very hard to see. It's all greater than 99%. It's a very significant fraction of the correlation energy is recovered. And there's some other trial wave functions that people use. So for instance, this yellow line is Sethanol. This is the Cambridge group, and they are doing a multideterminant expansion with backflow in it. And their VMC results are slightly better than ours. And the DMC results seem to be insensitive. Their DMC results are the same as ours for a slightly different trial wave function form. It's because of backflow, yeah. But at this time, there's no really nice way to do massive multi-determinant expansion and include backflow in it. That would be a very nice development, actually. Yeah. This is my last data slide. This is just going to look at this is from that same paper as the second one. This is the mean error in the mean average error in energies, total energies, for it like a benchmark set, the G2 set of molecules. These red lines in the middle are VMC. These blue lines are DMC. This green is couple cluster, single, double, perturbative, triple, with an F12 and basis set, different basis sets. And then these are without the F12 for a couple cluster, and these are MP2 results. So the thing to see here is just that as we increase the number of parameters in our trial wave function and optimize, it gets progressively better. In our extrapolated, so our DMC energies, errors and energies are better than everything else except for the rather large basis sets for the coupled cluster, single, double, perturbative, triple, and like the F12 corrections.
So what extrapolated means in tau or?
So this for us, the extrapolation means in the cutoff. So these parameters here, like 0.015, 0.0075, correspond, so you run a quantum chemistry calculation. This gives you a set of CSF, of configuration state functions. Each of these have parameters. And so you go through and you just say, okay, well, I'm just going to take all the CSFs that have parameters greater than some value. And as I decrease that value, I include more and more. And then I can extrapolate, use that to extrapolate to what if I included all of them.
But you have to assume some functional form for the extrapolation, I guess.
Yeah, that's true. I believe it's linear.
You mean inverse?
Yes. So, so that's, so this is
So
that.
how, if you really run it and you compare with the coupled cluster, computer-wise, what's the?
The efficiency?
Yeah.
I actually don't know the efficiency of coupled cluster very well. So I don't know how to, I apologize, but I just don't know.
No, but I mean, like for the systems where they've done, which one runs longer?
It's a good question. And so this is hopefully some things that we've learned today, how errors in wave functions affect observables, some history of wave function optimization, how the linear optimization works, and that optimization in QMC pack with multi-determinants give excellent results. Thank you.
Produced by OCE Atlas Digital Media at the University of Illinois, Urbana-Champaign.